In this lesson, we're going to look at lenses in combination. So how do we find image positions with two lenses? I want you to think about that and see if you come up with that answer, and we'll answer that in a moment. We look at the lenses one at a time. If you have two lenses right here, you first look at this first lens called the objective lens. You have an object here. Its image, first image, is right here at this location. Now you use this first image as the new object for this second lens, the eyepiece. So the image now becomes the object. And then you go ahead and do the exact same thing. You just treat this image as now the object, and you do your calculations to find out that this final image is way out here. The reason why that is because this first image, which is now the object, is inside the focal point. So you have to remember that when you work on this, you have to, if our object is over here, you have to first work with the lens that's closest to the object. You can't do both lenses at once. You can't do the second lens first. You have to do this first lens first and then the second lens second. Then you treat this image as the new object for the second lens. Then you calculate that image position. This will be the final image position. So here's our example of this. Here's our object way out here beyond the focal point. We draw a ray diagram to come up with our first image right here. It's a real image. It's inverted. It's larger. And now we draw, but it ends up being inside the focal point for this second lens, for lens 2. So we draw our new ray diagrams parallel to the principal axis, goes to the focal point. Then we draw our next ray right through here, right through the center of the lens. And this is a diverging situation. So we have to draw our rays back through the lens to find out our final image is virtual way over here. So let's look at a problem. We have the objective and eyepiece of a compound microscope are both converging lenses and have focal lengths of 15 millimeters and 25.5 millimeters. A distance of 61 millimeters separates the lenses. The microscope is being used to examine an object placed 24.1 millimeters in front of the objective. Find the final image distance. So here's a picture of our setup. This is the same picture we looked at before, but I just want to make sure we are all in agreement of how this is set up. And you don't have to have these light rays here, and you don't have to have this image right here. You just have to draw that this right here is 24.1 millimeters, and that the distance between the two lenses is 61 millimeters. Now let's go ahead and make our first calculation. We want to find out where our first image is going to end up, and so we have our distances and so on, and we use our equation, and we end up with our distance here of 39.7 millimeters. So this first image is 39.7 millimeters over here to the right-hand side. Now we want to compare it to the second lens and see what the final image position for that is. We're going to treat this first image now as our new object. So doing that, we use this as this first image, again, is our new object, so that's our object distance for this second lens. Our focal length is here, and we're going to use 1 over DO plus 1 over DI equals 1 over F again. And we end up with our image distance as a negative 130 millimeters, which we know is a virtual image, which means for a lens it's on the same side as the image. So it's going to be way over here, 130 millimeters over. So this is how you handle two lenses at once. They don't have to be both convex. You can have a concave lens in there as well. You can have mirrors, curved mirrors in there as well. But you would just handle it the exact same way you've handled it here. You just treat it, the first lens you just work with, find out where the new image is going to be, and then the next lens or mirror, you work with that to find out where that final image will be.